Welcome to the Physics Tutor. In this DVD course, we're going to discuss the fundamental concepts of physics, and we're going to do it without a bunch of boring lectures and a bunch of derivations that will take, 5 boards or whatever to do. But we're going to do it through working example problems, okay? I've taught a lot of people how to do algebra, calculus, trig, and also physics. And in my experience, it's actually the toughest subject to actually teach is really physics. And you might say, why is that? The reason that I've found that people have a tough time with physics is because most people have a tough time with word problems. And that is exactly what this course is. The entire course of physics is basically just a bunch of math problems that just happen to be word problems. You pick up a book of algebra or trigonometry or something, and you'll get a problem and it will say solve this equation. And then if you just know how to bang through the different steps, then you can kind of mechanically solve the equation and get the answer as long as you know the rules. Physics is a little bit different because physics we're gonna give you some rules, but it's not going to be clear how to get to the answer. It's not going to be clear what to do first, what to do second, what to do third. It's not going to be clear how to start the problem, okay? And so what I'm going to teach you in this course, I'm going to teach you in each section, I'm going to give you a kind of a basic lecture, a very cut to the chase, don't waste any time overview of the subject that we're talking about. And then I'm going to explain the actual mechanics of how to do the problems by doing problems. And one thing I want to say is that when you start a physics problem, or when I write a problem up here on the board, and you don't know immediately how to solve it, because most of the time you won't, don't freak out, okay? Everybody goes through that. You have to learn how to do this stuff by working the problems, okay? And if you stick with me and start at the beginning and work your way forward, I promise you that by the end of this DVD course, you will have a good understanding of physics and you'll have a good understanding of how to work problems in physics. So without wasting any more time, let's just get right to it. The first thing that we're going to talk about in this class is the first thing in almost every single physics book ever printed, and that's one-dimensional motion. Okay, that's generally going to be the first topic that you have in physics. Now, a lot of times, the very first topic will be a basic chapter that'll talk about, how do you convert units, what are the units in physics, what's the unit of force, what's the unit of distance, what's the unit of time, stuff like that. I chose to kind of skip that, not because it's not important, but I'm going to teach you that as we go and we work the problems. So if you don't know how to convert units, don't freak out. We're going to do that as we go along here. So what is one-dimensional motion anyway? We don't live in a one-dimensional world, okay? We live in a three-dimensional world as far as the 3 spatial dimensions. So in real life, like if this pen here is a basketball, okay, let's say, and I move it around, up and down, I can move it left and right, okay, that's one dimension. That's the, well, let's call it the x dimension, okay? I can also move it to you and from you, okay? And that's another dimension of space. We could call that the y dimension, let's say. Well, we can also have freedom of movement in this up and down direction here, and we can call that the z dimension, okay? They're just labels. It doesn't really matter. X, y, and z, okay? That's what we call three-dimensional motion. That's the real world, okay? When you go to the grocery store, or actually a better example is when you fly in an airplane, you might turn left, you might turn right, but you might also go up and down. So that's three-dimensional motion. When you start to learn physics, three-dimensional motion is too complicated. So you need to start out with one-dimensional motion. What does that mean? That means, imagine that there were a string across the screen here, just a regular piece of string, and there were some beads on that string, that kind of had a hole in them and they could slide back and forth, okay? One-dimensional motion just means motion constrained to move in only one dimension, because we're going to simplify the problems and we're going to look at the simplified version of the world, okay? So instead of talking about x and y and z, because that's pretty complicated, okay, and we're going to get there, let's don't do that at first. Let's start just by talking about one of those dimensions. And it doesn't matter which one. We usually just talk about the x dimension, okay? So this entire section is going to talk about how do things move when you describe the motion in one dimension, okay? So we're going to talk about the x dimension a lot. And just remember, that's just a label. It just means motion constrained in one direction only, backwards or forwards. No up, no down, no to and from just along this one line. Okay, so the first thing that we need to talk about is the concept of displacement. All right, now I ask you, what do you think that word means, displacement? Okay, displacement means to displace something, to move something, okay? That's exactly what it means. Physics is just going to define this formal definition of what displacement is. Okay, let's say, for the sake of argument, you had a ruler over here. Okay, this is a ruler, okay? And, I don't know, this is, you know, 0, 1, 2, 3, 4, 5, 6, something like that. Okay, this is just a measurement, like inches. This could be inches along the ruler, okay? And let's say you had some, I don't know, some fly or something like that, and it was sitting right here on top of the number 3, okay? And then over some period of time, the fly or the bug or whatever it is just kind of walks over to the right, and eventually it ends up over here at the number 6, okay? So here, I'm going to put an I here. This is where the bug starts, the initial position. That's why I put an I here. And over here, I'm just going to put an F because this is the final position of the bug, and it kind of walks over here, okay? Well, I should ask you a pretty simple question. How far did the bug move? Or in terms of physics, what was the bug's displacement, okay? Well, how far did it displace? It's pretty simple, okay? It started at 3, it ended up at 6, so I think you will all agree that the bug moved 3 units to the right, okay? So we say delta x is equal to 6 minus 3, which is just simply equal to 3. Now let me just stop for a second and explain what this means. I told you we're going to be talking about motion in one dimension, which most of the time we just use the label of x to describe motion in one dimension, motion along the x direction, okay? Now what does this delta thing mean? This is a Greek symbol, delta, and basically it just means change, okay? It just means change. When you see a delta there, it means the change in something. So I could have the change in the position along the x direction. I can have the change of the velocity of a car. I can have the change in the acceleration of a spaceship. I can have a change in a lot of different things. But anyway, this delta here, this triangle, it just means change. So anytime you see a triangle, all you have to do is put the word change in front of it, and then you will know exactly what that is trying to tell you. Okay, so we know from everyday life that delta x, which is the displacement, okay, is just 3. So I'm going to define displacement a little bit more formally in terms of physics, in terms of what you will see in a textbook. Delta x is equal to x final minus x initial, okay? Not too bad, right? I mean, this is exactly what we had here. I'm just generalizing it for you. I didn't want to throw this up on the board initially because, you know, some people are put off by formulas. Trying to show you from an example. So in order to find out how far something moved, all you do is you take the final position of that thing and subtract the initial position, and boom, you've got the displacement. You know how far it has moved, okay? The next thing we want to talk about is velocity, okay? You all know what the term velocity means. It means basically how fast is something moving, okay? The velocity of a car, the velocity of a spaceship. Very similar to the concept of speed. In fact, they're almost exactly the same. The only difference is the term velocity means that not only do you know how fast it's going, it means you know what direction it's going to. Are you going 5 miles an hour this way, or are you going 5 miles an hour this way? So speed would just be telling you how fast you're going, and velocity is how fast you're going and in what direction are you going. So most of the time we're going to talk about velocity because we're going to be trying to figure out in our problems, are we going this way or are we going this way, and how fast are we going. Okay, so that's basically what velocity is. I think we all have a fairly good understanding, big picture of what the term velocity actually means, okay? So to back up for 1 second, the unit of displacement is meters. Okay, as I said, we're going to talk about units as we go through this stuff in physics here, and so I'm teaching as we go. Unit of distance in physics that we typically use in books today is the unit of meters. Okay, is about 3 feet. A meter is about a yard, okay? So just deal in terms of meters. So the next thing we're going to talk about is velocity, which we already said is basically speed. So what is the unit of velocity? Well, in a car, you know that the unit is miles per hour, where miles is a unit of distance and hour is a unit of time. In physics, you're almost always going to be dealing in meters per second. Okay? And by the way, I'm putting this stuff in brackets because that's just my notation. I like to put the units in brackets because it kind of reminds me that they're separate, they're different. You just put them off to the side, put them in brackets, and that way you don't get mixed up and think this is some variable or something. It's not something you have to do, it's something I do. So the unit of velocity is meters per second in physics, okay? The next thing we're going to talk about is the concept of average velocity, okay? What if you had, I'm going to draw a plot here. This is time, the time axis, okay? And this is the x-axis. So remember, we're talking motion along one dimension. So as time goes on, I'm plotting the position of this little bead or whatever it is in this direction, like that. And let's just say that at the beginning of time, t is equal to 0 when I start looking at the whole environment here. I start out like this, and the plot looks something like that. And I'm going to explain this in a second. What this means is that when I started looking at my stopwatch, when I started looking at my bead that I'm looking at in my motion in this one dimension, I started moving pretty fast initially because if you look, as a function of time, I started to kind of move along x pretty quickly, but then as time went on, I kind of flattened down and I slowed down. Because you see over here, as time goes on, I'm not moving very far along x, okay? As you go along time in this region over here, I'm not moving very far along x, so I've kind of slowed down. Whereas initially, I was speeding up pretty fast because as time goes on here, I've actually covered quite a bit of distance along x, and so in the points in between here, I'm kind of slowing down. So basically what I'm doing here is I'm slowing down. So this motion would look something like this if you were to look at it. Okay, when I start off, I'm going pretty fast and then I'm slowing down like this. So let's look at it again. I'm going pretty fast and then I'm slowing down. Okay, it's just plotting the position as a function of the time. Okay, now at each point along this graph, I have a different velocity. Here I'm going pretty fast, relatively speaking, because as time goes on, I'm covering a lot of distance along x. And over here, and we've already talked about it, I've kind of slowed down. Now in the middle, obviously my velocity is changing. So the concept of the average velocity comes in here, and that's what I'm trying to tell you here. You can have motion that has a different velocity, you know, as you could be speeding, you could be slowing down, you could be speeding up, okay? So you can have different velocities all along your motion here, but you can also define what we call the average velocity, which is exactly what it sounds like. It's like, okay, you have this big picture motion going on, and you're changing your speed, but we can define in physics what we call the average velocity, which is kind of, if you look at the whole motion, what the average velocity is there along the motion. So we'll define that in terms of the velocity with the bar over it, which just means average velocity. And that's going to be equal to how far did I move, okay, totally, how far did I move from start to finish, and how long did it take me to move there, okay? So if I want to expand the top, delta x, remember I said delta just means final minus initial, so that's the final position minus the initial position, and delta t just means the change in the time, which is the final time minus the initial time. This is the definition for average velocity, okay? And if you also look at this, because we've defined it this way, the units of average velocity is also meters per second, because we have a unit of distance on the top and a unit of time on the bottom. And of course this fraction bar stays there, so meters per second makes sense with the units. What this means is that if you have a motion where your velocity is changing, all you do is you look at where you started, which in this case is the initial position here, where you ended up, which is the final position here, and how long did it take you to accomplish the motion, and then you just do this division and you can end up with the average velocity. And that basically means, on the whole, if you had to pick one constant speed to represent this changing speed here, then that would be the average. Sometimes you're going faster, sometimes you're going slower, but in the average, you can define an average velocity like this. And it only depends on the initial and the final values and how long it takes to get there. Okay? So, as an example, I mean, just as a really, quick and dirty, simple example, okay, which I'll just kind of write right here. Let's say you travel some distance, along the x-axis of, let's say, 10 feet, and we almost never deal with feet in physics, but in this case I'm just going to do it just for the heck of it. And how long does it take you to go 10 feet? It takes you 2 seconds to go 10 feet. So then you can define an average velocity, which is just going to be delta x over delta t, and that's just a fancy way of saying how far did you move in the x direction. I've already given you that, that's 10. And how long did it take you to do that? It took you 2 seconds. You do this division and you get an answer of 5. But you've always got to be clear. 5 what? Well, I was dividing feet by seconds, so it's going to be feet per second. Okay? Okay, good deal. Now we're going to work a little bit different kind of problem. We're going to get some practice with converting units. Okay? We're going to get some practice with converting units, and we're going to get some practice with some of this initial final velocity stuff. Okay, you have a problem at the bottom of your screen now. And basically the problem says that for a marathon, there's a record out there that says it takes someone 2 hours, 9 minutes, and 21 seconds to do this marathon, and the distance is 26 miles, 385 yards. So what we need to determine the speed, okay, which is basically like the velocity, in miles per hour. That's what we want to solve for. Okay, and what we're given is that the time is 2 hours, 9 minutes, 21 seconds. Let's make this clear here. 21 seconds. And the distance is 26 miles, 385 yards. And we're trying to find the answer here in miles per hour. And this is basically a problem in unit conversions here. And we're also going to use the formula for speed. Okay? So we know that speed, or basically velocity, like I said, they're almost exactly the same concepts, is going to be distance over time. It's another way of saying delta x over delta t. This is just the change in your distance, the change in the time. Okay, so we're given this information. We know the distance, we know the time. So what's the big problem here? Well, obviously, the problem is we're given the distance in miles, 26 miles, and then 385 yards. So this is much smaller than a mile. And the time is given in hours, minutes, and seconds, and we want to compute things in hours. So what we really need to do in order to solve this problem, in order to get the final units we want, is to convert this distance into miles. Okay, so there's no yards anymore, it's just miles. And then also to convert this time to hours, and then we'll have miles, and then we'll have hours, and we can simply divide them, we'll get miles per hour, right? So let's go ahead and do that. For the distance, okay, we already have 26 miles. Okay, so we're going to hang on to that for a second. What we want to do is we want to convert this 385 yards to miles. So 385 yards, okay, that's what we're starting with. And what we want to convert is this yards to miles. Now I'm going to show you a trick. This is probably one of the most useful things that I'm going to teach you in the whole class on how to convert units, is this right here. It's not really a trick, it's just the actual way in which you convert units. You're starting with yards, and you want to get to miles, okay? What I'm going to show you how to do is the following. I'm going to write it on the board. You may not quite understand it, but then I'm going to explain it as we go. Okay? What I know is that 1 yard is equal to 3 feet. That's something that you should know or that you probably could look up. Okay? What I also know is that 1 mile is equal to 5,280 feet. Okay? And this is going to allow me to convert yards to miles. How? Because, and again, you may not quite understand this yet. I'm going to explain it to you here in just a second. These yards cancel with these yards. These feet cancels with these feet. So in the end, if I were to take the 385 times the 3 divided by, because it's on the bottom, divided by the 5280, then the only thing left is the miles, because the yards went out with the yards, the feet went out with the feet. What I've done here is I've set up a set of conversion factors. What you do is you write down what you start with, you draw your little horizontal line, and then you start picking conversion factors in order to cancel what you don't want to have in the end, which is yards. We want to get rid of yards. I knew I had to go from yards to miles, but I didn't really know off the top of my head how many yards were in a mile, so I kind of did it in 2 steps. Yards to feet, feet to miles, and arrange them. You know, if I would have put this on the top, the 5280 on the top, feet, and the miles on the bottom, then I wouldn't have canceled the feet, because I would have feet up here and feet over here, and I wouldn't be able to cancel. In order to cancel, you have to have 1 on the top and 1 on the bottom. Okay? And we're going to do this over and over again, so you're going to get the hang of it. Essentially, when you do this, 385 times 3 divided by 5280 is going to give you a grand total of 0.21875 miles. Okay? And this is how many miles 385 yards is equal to. So the total distance is equal to the 26 miles I had to start with, plus this 21875. Okay, so in the end, the distance is 26.219 miles, and I'm kind of rounding a little bit here. So what we've done is we've taken the 26 miles, 385 yards, we've converted that to 26.219 miles. The 385 yards gives you 0.219 miles, okay? Now for the time, and we're going to do the same thing here, and I think you'll get the hang of it. I want to end up with hours. I've got hours, minutes, and seconds. So what I need to do is convert minutes and seconds into hours, and then I can have the entire thing in hours. So let's start with the seconds first. 21 seconds, and I want to convert to hours, okay? Now, I know that 1 minute is equal to 60 seconds, so I'm going to put 1 minute up on the top, 60 seconds on the bottom. Why did I put seconds on the bottom? Because what I want to do is I want to cancel the seconds, so I want to take this and cancel it with that. But I don't want to stop at minutes, because what the whole point of this was trying to get over to hours. So what I'm going to do is I'm going to say there's also 60 minutes and 1 hour. Why did I put the minutes on the bottom and the hours on the top? Because I wanted to cancel minutes with minutes. Now, I started with seconds, and everything else is canceled, and I've just got hours left over. So if I take 21 divided by 60 divided by another 60, so 21 divided by 60 divided by 60, I will get 0.0058, and that is hours. Okay? That's how many hours 21 seconds is equal to. Now let's work on the minutes. 9 minutes, 9 minutes, okay? 60 minutes and 1 hour, okay? And that's really all I have to do, because minutes cancels with minutes, so I'm converting 9 minutes to hours. So 9 times 1 divided by 60 is 0.15 hour, okay? So let's not lose track of the big picture. The time is 2 hours, 9 minutes, 21 seconds. 21 seconds is equal to this many hours. 9 minutes is equal to this many hours. So the total time is equal to 2 hours that I started with, plus the 9 minutes, which is equal to 0.15, plus the 21 seconds. 21 seconds is equal to this, 0.0058. So the total time is 2.1558 hours. Okay? That's the total time. Now, I did all this mess. Why? Because it's an exercise in how to convert units. I want to calculate the speed in miles per hour, so I need to have some distance in miles, and now I have that, which is right here. This is how many miles I traveled. And I need to have time in hours, which is this many hours right here. All right. So the answer, which I'm going to kind of work on kind of right here, the velocity is equal to distance over time, which is equal to 26.219 divided by time, which is 2.1558, and this is in miles and this is in hours. So then the final deal here is going to be 12.2 miles per hour. Okay, that was a lot of junk thrown on the board. We had time, we had distance, we just had to convert various things into miles and into hours. When we had the miles and we had the hours, we could divide the two and we get miles per hour. Okay, and I think you can see that, you know, by working these kinds of problems, that physics is going to be kind of like that. I mean, in general, it's really going to be a bunch of tedious stuff. And really, you know, that was a fairly simple problem, fairly mechanical. We knew basically what to do, okay? And as you go on, sometimes it's not going to be clear what to do. So the challenge is going to be figuring out what to do. The next thing I want to talk about is the concept of acceleration and also average acceleration. You know, a minute ago we've talked about position and displacement, okay? We've talked about velocity and we've talked about average velocity. Now we're going to talk about acceleration. Acceleration is the phenomenon that you have whenever you're speeding up and you're slowing down. So if you're kind of moving along at a constant speed here, you don't have any acceleration. Your acceleration is 0. If you're speeding up or you're slowing down, you are accelerating, just like in your car, okay? So then you can also define an average acceleration, just like we could define an average velocity, and so we'll write that as acceleration with a bar over it. And that one's equal to the change in velocity over the change in time, the same as what we had talked about before. So this will be the final velocity minus the initial velocity over the final time minus the initial time. And of course, velocity, the units of velocity we've already talked about is in meters per second. Okay, and for the units, the unit of time on the bottom is seconds. So what you can write this as is meters per second times 1 over second. Meters per second, which is this quantity here, times 1 over seconds, because the s is on the bottom. So what you end up with is meters per second squared. And that's why you see in your book the units of acceleration as meters per second squared. Exactly because of this right here. Okay? So if I were going to kind of plot what this is really talking about, then you would have some time, and then you would have some velocity. And then if you were going to start looking here, you know, you would kind of have the velocity would be going up and then going down and going up. So basically here you're accelerating, and then here you're turning back around and going the other way, and then here you're accelerating again and you're going back the other way. So obviously your velocity is changing here. You're speeding up, you're slowing down, etc. But if you were going to define some average velocity, it would depend only upon the endpoints here, because it only depends on the initial and the final values. And what you're doing here is you have some complicated motion where you're speeding up and you're slowing down. But on the whole, on the average, you might be speeding up, you might be slowing down, but there's an average acceleration to it. So you can define an average quantity that'll describe the big picture here. And it's only going to depend on the initial and the final value, which is exactly what we have right there. Okay? So let's do another problem. Okay, in this problem, we're going to send a man to the moon, and we're going to do it in a really weird way. We have a cannon, basically, and we're going to shoot this guy out of a cannon. And you see his final velocity is 10.97 kilometers per second, and the cannon is 220 meters long. And so what we want to do is we really want to find out how fast is that guy accelerating out of the cannon here, okay? Now I might also just mention that in your physics book you'll probably see a lot of this stuff. Here we're dealing in terms of kilometers, okay? We've been talking about meters this far. A meter is about that big, just about, you know, just off the screen here. It's about 3 feet or so. Okay, a kilometer is a kilometer, which is 1,000 meters. So it's pretty far a little distance here. I'm just trying to give you a scale for what we're talking about here. First thing we need to do when you're confronted with any physics problem, the number one thing you need to do is draw a picture. Most people, if you just draw the picture, the solution will kind of pop out. So what we do is we have a cannon here. This is the wheel, I guess you'd say, of a cannon. I'm not a real big artist here. But you have some cannon, right, like this, okay? And this cannon is a pretty big cannon. It's 220 meters long, okay? And then you've got some guy that I'm just going to put out here like this that pops out of the cannon. He's shot out of the cannon, and he's shot out at a final velocity of 10.97 kilometers per second, okay? So he's shot out of the cannon, boom, he's flying out 10.97 kilometers per second. That's pretty fast when you think about it. 10 kilometers every second. I mean, that's like, you know, really, really fast, okay? Obviously, when he was inside the cannon over here, okay, his initial velocity was just 0. Okay, he wasn't moving when he started. Okay, when he was in the cannon initially, he wasn't moving at all. And then, boom, the cannon fires. He is then accelerated down this guy right here. He is accelerated faster and faster and faster and faster. Finally, he pops out and goes off to the moon. Okay. What we want to do is we want to figure out what is the what is the acceleration, or another way to say that, what is the average acceleration that this guy experienced. In other words, here he started to speed up and he popped out of the cannon. What we want to do is we want to figure out what is the average acceleration. Now, I've already given you the basic big picture formula for that, and that is delta V delta T. So all we got to do is we got to figure out how fast, you know, well, let me just blow it up here. This is the final velocity minus the initial velocity, final time minus the initial time, okay? So if we know the initial and final velocities and we know how long it took him to get to the end, then we can calculate his average acceleration, okay? So let's see if we can do that. His final velocity is the velocity that he had when he popped out the other side of the cannon, so it's 10.97. The initial velocity, we already said, was 0. Now, how long did it take him to actually travel down to the end of the cannon? What's his final time and his initial time? In other words, how long did it take him to actually do this? Well, obviously, there's nothing in the problem. There's nothing in the problem that tells you that, okay? And so you might be stumped. This is a great example of in physics when you start scratching your head and you're like, I don't know what to do now because they didn't give me enough information. And then you start to say, well, maybe there's a problem with the problem. Maybe the book made a mistake. Maybe they didn't give me what I need to know. Don't fall for that stuff, okay? There's always enough information, 99% of the time, for you to figure out what you need to figure out, okay? I deliberately worked the problem like this to kind of go in logical order to show you how you can reach a point when you don't know what to do next, okay? So what we need to do now is start looking at the problem a little more carefully and figure out how can we figure out the time it took this guy to go from one end to the next, okay? Take note that, I'm going to draw a little line here, we're going to come back to this point and find this time right now. Notice that we know the final velocity of this guy is 10.97, the initial velocity is 0. So we know he starts at 0 and he accelerates to a final velocity, okay? So if you assume that his acceleration was uniform, in other words, he kind of uniformly accelerated up this tube, then you might be able to say that the average velocity here, how fast on average was he traveling down the tube, is just simply going to be the average of these two numbers. So VF plus VI over 2. That's literally the definition of an average. You take two numbers and you add them together and you divide by 2. So 10.97 plus 0 divided by 2. And when you put this in your calculator, you will get 5.485 kilometers per second. Okay? So initial velocity, final velocity. Average velocity is, on average, how fast was he traveling. Sometimes he was going faster, sometimes he was going slower, but this is the average. Okay? So if this is the average speed, and this is the length of the tube, then we can use these two numbers to calculate how long it takes him to go to the end. Now remember, velocity is equal to distance over time. Okay? So time, by rearranging this equation, is equal to distance over velocity. And you can see that because this is an equation like any other equation. I can multiply both sides by t, okay? And so I'll have vt is equal to d if I multiply both sides by t. And then to solve for time, I can just divide by v. So I get t is equal to d over v. So I just solved this equation for time. That's all I did there. I'm just trying to calculate the time here. Okay? And I know the distance the guy traveled. I know his average velocity. I can calculate the time. Okay, so the time is equal to distance over velocity. So what we want to do is we want to solve for the time. Okay? But what we want to do is the distance, the length of this tube is 220 meters, but I don't want to put 220 in this equation, because if I put 220 meters in this equation, okay, and then divide it by this velocity is in kilometers per second, you see? And so what I'm trying to do is I'm trying to arrive at a unit of seconds. I'm trying to get the time out. And I have incompatible units here because I've got the tube in meters and I've got the velocity in kilometers per second, and that's not going to wash. First thing you have to notice, first rule of physics, is the units have to be consistent. So I need to either convert this to meters per second or I need to convert this to kilometers. And it's easy for me to convert this to kilometers. So I'm just going to put a decimal point here, 220. And this is kilometers. And then the velocity is 5.485, and this is kilometers per second. Now the kilometers will cancel, the seconds will flip back onto the top, and in the end, the time it takes this guy to pop out the tube is 0.04 seconds. Okay? One thing I'm going to explain to you real fast, 220 meters you can convert just like anything else. You have to use a conversion factor, so 1,000 meters is 1 kilometer. Okay? Same as everything else. You take the 220, you divide by 1,000, and that gives you 0.220 kilometers. You know, I kind of did that in my head there, but I want to explain to you where it comes from. So, don't forget the big picture. We knew the initial and final velocities here. We needed to calculate the time. In order to calculate the time, we calculated an average speed for this guy flying down the tube, which is just the average of the initial and final velocities, and we knew the distance of the tube, so knowing the formula velocity is distance over time, then we basically plugged in everything and we solved for time. Comes out to 0.04 seconds. Okay? So we put that in like this, and then the acceleration. Okay, so on the top we have 10.97 minus 0, and this is in kilometers. The bottom is in terms of seconds, so the average acceleration of this guy down the tube is 10.97 divided by 0.04, which is 274.25 kilometers per second. Okay, so you put a guy in a cannon, you shoot him out the end, and he's going at an acceleration of 274.25 kilometers per second squared. The units is kilometers per second squared because I had velocity on the top, kilometers per second, time on the bottom, so I have kilometers per second, which is this guy. Now, if you wanted to compare this to something that's familiar to you, the acceleration of gravity, the acceleration due to gravity is called g, okay? The acceleration that holds us to the ground is 9.8 meters per second squared. Okay, of course this is meters per second squared, this is kilometers per second squared. So how would you compare those two numbers? 274.25 kilometers per second squared. I'm going to convert this to meters per second squared. 1 kilometer is 1,000 meters. So kilometers cancels with kilometers. So this acceleration, basically you just multiply by 1,000. So you have 274.250 meters per second squared. Now these are the same two numbers, okay? This is just in terms of kilometers per second squared, and this is in meters per second squared. I just converted it to show you that look at how incredibly huge this number is compared to the acceleration of gravity, the gravity that's holding me right now on the floor talking to you today, okay? So shooting yourself out of a cannon is a pretty dangerous thing, and it would kill anybody obviously doing that. In terms of this problem right here.